Okay, we've been talking all this week about relations. Today, we want to talk about a very special class of relations called equivalence relations. These are very important in mathematics. And as you might guess from the name, they are the way that we formalize the notion of equivalence of objects. Let's get on to equivalence relations right now. Let R be a relation on A. Remember, this means that it is a subset of A cross A. We say that R is reflexive if A comma A is in the relation for any A in A. We say that the relation is symmetric if for any AB in A, if the pair AB is in R, then the pair BA is in R. Said another way, a relation is symmetric if its symmetric conjugate gives us back the same relation. Finally, we say a relation is transitive if for any ABC in the set A, whenever the pair AB is in R and the pair BC is in R, then we get that the pair AC is in R. A relation that is reflexive, symmetric, and transitive is called an equivalence relation. When R is an equivalence relation, we sometimes write it with this little curly line, which is \sim in LaTeX. Here's some examples. Recall from last time, we talked about the diagonal relation, which is the set of all pairs AA when A ranges over A. That's an equivalence relation, which is pretty easy to see. Here's another example. Let's let A be the integers, and we say that x relates to y if and only if y minus x is even, which is equivalent to saying 2 divides y minus x, which is of course equivalent to saying that x equals y mod 2. That's certainly a relation, but is it an equivalence relation? Let's check. Number 1, is it reflexive? Does x relate to x? Well, notice that x minus x is 0, 2 divides 0, anything divides 0, so it's reflexive. Let's try symmetric. Well, notice if x minus y is even, then y minus x is even. Now, finally, let's look at transitive. Let's assume that the pair xy is in the relation and the pair yz is in the relation. That means, by definition, that y minus x is even and z minus y is even. But notice that if we add y minus x to z minus y, the y's cancel and we get z minus x. And even plus even is even. Therefore, if x comma y is in the relation and y comma z is in the relation, then x comma z is in the relation. And we've gotten transitive. Putting all those together, this must be an equivalence relation. Now we'll consider a few more examples. Here's an example that doesn't look super mathematical. Let A be the set of all human beings. And let's define R, a relation on A, to say that it contains all pairs x and y such that x and y were born in the same calendar year. I claim that this is an equivalence relation. Let's check. First of all, is it reflexive? And yes, every person is born in the same year as themselves. Is it symmetric? Yeah. If x and y were born in the same year, then y and x were born in the same year. And finally, it is transitive. If x and y are born in the same year, and y and z are born in the same year, then x and z are born in the same year. All right, another example. Let's let A be the real numbers, and let's define the less than or equals to relation. So R is the set of all pairs of real numbers x, y, such that x is less than or equal to y. Is this an equivalence relation? Let's go through. First of all, is it reflexive? Yes. For any x, x is less than or equal to x, so it is reflexive. Is it symmetric? It turns out it's not symmetric. X can be less than or equal to y, and y not be less than or equal to x. For example, the pair 1, 2 is in R, and the pair 2, 1 is not in R. It turns out that this is transitive. We could check that, but since we already lost symmetric, we're done. This is not an equivalence relation. Here's a trickier example. Let's let A be the set of all lines living in the plane R2. And let's say that L1 relates to L2 if L1 and L2 intersect. Okay, is that an equivalence relation? Let's go through the properties. Is it reflexive? Turns out it is. Every line intersects itself. Is it symmetric? Yeah, it turns out it is. If L1 intersects L2, then L2 intersects L1. Now let's check transitive. It turns out that it's not transitive. It's possible for L1 to intersect L2 and L2 to intersect L3, but L1 does not intersect L3. For example, as we could draw in this picture, L1 and L3 could be parallel, and yet L2 could intersect both of them. So L1 relates to L2, L2 relates to L3, but L1 does not relate to L3. Therefore, this is not an equivalence relation. Okay, one more example. Let A be the set of real numbers, and let's say that x relates to y if x squared equals y squared. Is this an equivalence relation? Let's check reflexive. Notice for any x squared equals x squared, so yeah, it's reflexive. Notice that if x squared equals y squared, then y squared equals x squared, so it's symmetric. Now finally, note that if x squared equals y squared and y squared equals z squared, then x squared equals z squared, so it's transitive. Okay, now a definition. Let's let squiggle be an equivalence relation on A. Then the equivalence class of x, some point in A, is written as square bracket around x. It is all the y's that relate to it. Another way of saying this is that the point y is in the equivalence class of x if and only if y relates to x. We can also define the quotient of A with respect to the relation, sometimes written as A/relation or said A mod relation, as the collection of equivalence classes. Remember, we talked about collections of sets, so for every x, we get a set, bracket x, which is the equivalence class of x, and then we can collect all of those equivalence classes for every point in A. Let's revisit this example we did a minute ago. Let A be the integers, and let's say that x relates to y if and only if x minus y is even. We showed earlier that this is an equivalence relation. Now let's think about what the equivalence classes are. What is the equivalence class of the point 0? Well, it's any point that's even. So the equivalence class of 0 is the set of even numbers. What's the equivalence class of 1? Well, it's any number such that that minus 1 is even, so of course it's any odd number. So the equivalence class of 0 is the even numbers, the equivalence class of 1 is the odd numbers. But notice, there are more equivalence classes floating around, they just match the ones we've already given. For example, the equivalence class containing 0 is the same as the equivalence class containing 2, which is the same as the equivalence class containing 4, etc., and these are all the even numbers. In particular, if you pick any even number, the equivalence class containing that even number is the set of all even numbers. Similarly, if you pick any odd number, the equivalence class containing that odd number is all of the odd numbers. So what do we have when we look at Z mod this equivalence relation? Notice there's really only two sets floating around, the even numbers and the odd numbers. So what we have is Z mod equivalence is the two-element set, each of which is its own set, the evens and the odds. Notice in this particular case, we have this nice property that if we take any two integers, then one of two things are true. Either the equivalence class containing m is exactly equal to the equivalence class containing n, or the equivalence class of m and n are disjoint. So in other words, if m and n are both odd or both even, if they have the same parity, they have exactly the same equivalence class. If they have opposite parities, their equivalence classes do not intersect at all. Let's revisit that earlier example where we let A be the set of all humans and say x relates to y if they're born in the same year. We showed earlier that this is an equivalence relation. What do the equivalence classes look like? Well, notice if I take any person born in, say, 1972, to pick a year at random, the equivalence class of that person is the set of all people born in 1972. If, for example, I pick one particular person born in 2001, then the equivalence class of that person is the set of all people born in the year 2001. So there's kind of a correspondence between the equivalence classes and years here. Said another way, if we take A mod this equivalence, we can parameterize all these sets just by years. Just list the years, and for every year, consider the set of all people born in that year. Okay, let's revisit another earlier example where we took a to be the set of reals and x relates to y if and only if x squared equals y squared. We showed that this is an equivalence relation. Let's think about what the equivalence classes look like. First of all, what is the equivalence class containing 0? Well, the only point equivalent to 0 is actually 0 itself, because we get the equation x squared equals 0 and there's only one solution. So the equivalence class containing 0 is a single point containing the number 0. However, let's take any other number. If I take any real number r that's not equal to 0, notice that the equivalence class containing r actually has 2 points, r and minus r. So if we look at A mod this equivalence, it's got this complicated description as having one singleton set containing 0 and then a union over positive reals of a 2-element set, r, minus r. Okay, now one thing you might have noticed. In all the examples we've talked about so far, when we looked at the equivalence classes under some equivalence relation, we always had this property that if you take any 2 points in the set, x and y, then either the equivalence class containing x was exactly equal to the equivalence class containing y, or these two equivalence classes had an empty intersection. It turns out that this is a general principle that we're going to discuss next time. Okay, a couple more examples and we're out. Let's let A be the set of positive rational numbers, or written as Q+. Now, take any two numbers in Q+, and let us say that x relates to y if and only if the quotient y over x is some power of 2. And notice, I'm letting any power, it could be a positive, negative, or 0 power. Is this an equivalence relation? Well, let's check. It's reflexive because if I take x equal to y, then x divided by x is 1, which is 2 to the 0. So for any x, x relates to itself. Let's check symmetric. If x relates to y, that means y over x is 2 to the m by definition, but then of course x over y is 2 to the minus m. Since we allow both positive and negative powers, this means y relates to x, so we get symmetry. Now finally, let's assume that x relates to y and y relates to z. If x relates to y, then y over x is 2 to the m. If y relates to z, then z over y is 2 to the l. Therefore, z over x is z over y times y over z, which is 2 to the l times 2 to the m, which is 2 to the l plus m. So we get transitive. Since we have an equivalence relation, we have equivalence classes. Let's pick a particular number in Q+, remember, a positive rational number. What is the equivalence class containing the number r? Remember that y is in r if and only if y relates to r, if and only if, by definition, y over r is equal to 2 to the m for some integer m, which is the same as saying y equals 2 to the m times r for m an integer. This gives us a parameterization of this equivalence class. The equivalence class containing r can be written as the union over the integers of the single point sets 2 to the m times r. One last example before we go. Let's let A be the set of real numbers, and let's say that x relates to y if and only if the absolute value of y minus x is less than or equal to 1. Is this an equivalence relation? Well, it's certainly reflexive, right? Because x minus x is 0, is an absolute value of 0, and that's less than 1. So check. Also notice that the formula itself is symmetric with respect to y and x. If the absolute value of y minus x is less than or equal to 1, then the absolute value of x minus y is exactly the absolute value of y minus x, so it is, of course, less than or equal to 1. However, this relation is not going to be transitive. To see this, let's try to go ahead and prove it and see what goes wrong. Let's say x relates to y and y relates to z. That means that the absolute value of y minus x is less than or equal to 1. The absolute value of z minus y is less than or equal to 1. So let's compute the absolute value of z minus x. Noting that we can write z minus x as z minus y plus y minus x, we get that the absolute value of z minus x is the absolute value of z minus y plus y minus x. Using the triangle inequality, that's less than or equal to the absolute value of z minus y plus the absolute value of y minus x, which is less than or equal to 1 plus 1. But wait a second, we don't get a bound of 1, we get a bound of 2. So this estimate has failed. Now, the fact that the estimate has failed doesn't imply that it's not transitive, but it should give a warning sign to us that this thing's probably not transitive. And in particular, let's think of an example. If I take the 3 points x equals 0, y equals 1, z equals 2, we can see that x relates to y, because the difference is less than or equal to 1. Y relates to z because the difference is less than or equal to 1, but the distance between x and z is 2, so it fails. This relation is not transitive, so what that particular means is it doesn't make sense to talk about the equivalence classes with respect to this relation because it's not an equivalence relation. Let's stop there.